Thank you for watching this video, which concerns the first lecture on the chapter 2 on course laser physics. So I will just start briefly by motivating slightly what this chapter 3 is about. So essentially we are describing passive optical resonators now on our chapter in the upcoming 7 or so lectures. So we have so far gone through the basics of laser physics, introductory concepts. So essentially how we can pump our gain medium. Then in the second chapter, we described how we can really understand from the quantum mechanical point of view what happens in terms of light matter interaction, so how this pumping actually takes place. And now we are more into kind of interested in moving into the description of actual laser cavity, so how that gain medium actually will be placed within a laser resonator and how we can make that resonator system to oscillate. So that's basically the kind of main point regarding this chapter 3 material. And I will start this lecture by going into description of the matrix formulation of paraxial optics. So essentially we will introduce to you so-called ABCD matrix formalism that can be used to understand how rays are propagating within a system. So basically, our focus, of course, is in laser resonators, but of course, be warned that this kind of ABCD matrix system can be used to understand many optical systems. So it doesn't just be restricted to laser physics, but it's far more general in coverage. And I will just warn you that we will be using this very extensively, this mathematical formalism, but especially this connects directly into stability condition analysis, eigenmodes of optical resonators, and so forth. So basically, what you will be discovering in this lecture will be extremely useful mathematics for you in what follows. Not just in this course, but also in other parts of your hopefully long lives. So I will now just get started with the actual material. So what we are doing now is that we are really focusing on a very important element common to all lasers, and that's essentially the cavity. And how do we understand the cavity, how it functions? We want to, first of all, simplify our treatment. So we just assume that paraxial approximation holds, which implies that we can now treat the field, the electromagnetic field inside the cavity, basically as a collection of rays, geometrical rays, as we remember from the basic optic course regarding geometrical optics. And this is most of the time extremely good approximation. We don't really need to be dealing with real a field propagation most of the time. I guess the kind of first stages where this approximation starts failing is that when we really go into very small laser cavities, microcavities, vertical cavity, semiconductor external lasers, so VEXELs, and that kind of systems or microresonators, then we start to really be looking into the kind of field propagation in a real kind of field quantity, or when we are looking more carefully into the transverse modes that take place within laser resonators. But most of the time, we don't really need to be going that much further in our treatment beyond the paraxial approximation and using geometrical optics to describe what happens for the propagation of light. Okay, so how we can really justify this on a text. The field inside a cavity propagates mostly as a collimated beam. So basically that implies that all the rays stay more or less parallel to the optical axis. Then we are really mostly interested here in the longitudinal propagation features of the field. So basically we are not that much interested in the transverse structure of propagating fields. That kind of treatment can be really done with rigorous diffraction theory, but that's more or less beyond our interest right now. We can understand how transverse modes arise in laser resonators by using more ad hoc theory. We don't need to be forming a really rigorous mathematical theory to understand how that kind of modes arise in these kind of laser resonators. But in any case, if you're really interested, please have a look on Svelto's book, how the mathematics will be generalized. But most of the time, we are really interested in longitudinal propagation, longitudinal features, longitudinal modes of the laser resonators, and that motivates us to kind of restrict our treatment to ABCD matrix formalism. And how do we start is that we will determine a geometrical ray, by using two variables. So first of all, the position away from the optical axis, the z-axis, so that position is denoted with the y coordinate, and then the angle alpha that is formed with respect to the ray and the z-axis, so that's the optical axis. So that's basically figure describing what happens and how we are describing a ray propagating through an optical system. So first of all, we start at a given plane by denoting that the distance from the optical axis is denoted with parameter y, and the ray that would be propagating from here onwards would be propagating at an angle of alpha on this plane of z1. And then after propagation, when we are looking at the ray at a z2 plane, then we have a y prime coordinate denoting what is the distance from the optical axis, and then we might have a different angle alpha prime describing the angle with respect to the optical axis. So that would be the z-axis in this picture. So if you want to describe a propagation of light ray or ray of light through an optical system, we can really simplify the treatment into a very simple matrix vector multiplications. So we can calculate this y prime alpha prime vector as a function of the input vector, so denoted that with a y and alpha variables by suitable modeling of optical systems. So essentially that just means that we will describe this kind of propagation of light using A, B, C, D matrices. So essentially 2 times 2 matrices where each index is labeled as A, B, C, or D. And where this kind of treatment can be used, we can, for example, understand ray propagation through more complicated systems. So for example, collection of mirrors, collection of lenses, and understanding how the imaging is being formed, understanding how much of light we are losing, doing, for example, imaging using multiple lenses and so forth, how the rays actually are propagating through this kind of more complicated optical system. And then more connected to our actual curriculum on this course, we can understand, for example, laser resonator stability by using this kind of ABCD matrix formalism. So we may be interested in trying to understand how a ray is being propagating through the optical system, and after a round trip, we would be interested in seeing does the ray of light propagate or return to the original starting position and angle, or does it go elsewhere? So in other words, is the laser resonator configuration stable or not? So that would be our question we are looking into in our following lecture on 3.4. Okay, so let's get forward. The propagation of rays through a system follows a simple linear algebra. So essentially that would be a matrix vector multiplication. So we have our output vector, and how do we get into this output vector is that we multiply our input vector with this kind of A, B, C, D matrix. So that's a 2 times 2 matrix, and then we have our input vector y alpha here. Here the y primed vector, so y prime and alpha prime vector is an output ray, and then this ABCD matrix is the matrix that describes how the optical system transforms the input ray, and the input ray is being denoted with these variables y and alpha. And please note that this ABCD matrix only describes ray propagation from an input plane that sometimes is being described as pi in, as an input, to an output plane of pi out, as Svelto uses in his notation in the book. So strictly speaking, this vector matrix vector multiplication doesn't really tell us how the ray is propagating in between these two planes. So for there, we would need to be doing a little bit more, for example, these kind of matrix vector multiplications to really build the propagation of ray in small infinitesimally thin slices of material. But in this usual formalism, we only tell, or we can only calculate how the ray gets transformed when it's transmitted through the system. But as such, this matrix vector multiplication, of course, does say nothing about how the ray propagates in between these two planes. If the position of either of these planes changes, so then we also must change the matrix accordingly. And this is related to the above previous point. So like this ABCD matrix really only relates given input ray in a given plane into an output ray in a given plane, so these two planes of interest. And if we somehow change these planes, of course the whole matrix description changes, so please remember this in what follows. Then something about the conventions, so basically about the signs of variables. So we usually like to describe propagation of rays of light and propagation of light along the positive z axis. So basically plus z direction is being taken as the propagation direction of the ray. That's usually how we like to describe our ray propagation. And when a reflection happens, then the z greater than 0 condition is being inverted because the ray propagation is being inverted. So in that case, then the propagation is along minus z direction. So for example, when we would have rays hitting a mirror, and then we would be looking at the ray propagation afterwards, then we must be careful with the sign notation. Then about mirror curvatures, they are defined as follows. So if we have a concave mirror, then the radius of curvature is defined to be positive, and for convex mirrors, we define that the radius of curvature is negative. And this convention is consistent with the definition that we have a propagation along the positive z direction. Now let's get started with the actual like a derivation or illustration of the ABCD matrices of simple systems. And let's start with the simplest, so essentially a free propagation within a medium of air. So let's go through these few examples, and then we know roughly how we can only really start calculating system analysis for laser resonators. So most common ABCD matrices, let's go through these. And then the first one in line is the free propagation, and we start with that. So we let a ray propagate a length of L within free space. And then in this case, we are describing the situation, the ray propagation schematically using this kind of figure. So we start with a given plane Z1. We have a given angle alpha here. Then we have a given displacement from the optical axis. And then the ray just happily propagates in air because there's no refractive index change within this interface. So that's what happens. And we are interested in a propagation of length L. So that separation, the length between the two planes of interest equals L, as shown in this picture and how I was describing things earlier. So the ABCD matrix essentially of free space is something like this, and you can like check out that it works out like that. So that's basically how we describe what happens. So the angle is not being changed. The only thing that changed is that we have the distance from the optical axis being modified, and that depends linearly on the length of our medium of interest. So if you like plug in this kind of a matrix, multiply that with the input vector, you can see that you get out the output vector that corresponds to the kind of vector that you would suspect that you would get by just looking at that figure. Now, let's complicate things. Similarly, we can really consider propagation of length L in a medium, but now we have a refractive index N within that medium. And now the ABCD matrix is given in a similar way, but the only change is that now we really have a refractive index modifying the B component in our matrix component here. So essentially, we again have propagation, but we have the refractive index N modifying that the ray of light is actually not being propagating at the same angle at which the ray hits the Z1 plane. So basically, like hopefully this figure clarifies to you what happens. So we start with a ray, the ray hits an interface, the refractive index is being changed, so we have more optically dense material through which the ray is propagating, and due to the fact we have refraction taking place so that the angle is being modified. But afterwards, of course, we are returning to the original medium, so the angle will be the original alpha. So in that respect, there will be no modifications. So the only modification is to the displacement y prime. That tells us the displacement with respect to the optical axis. And basically, we see that the only thing that gets modified is this component here in the matrix. So I hope that these two figures make sense, and then you now can understand how free space propagation takes place using this kind of ABCD matrix formalism. Now let's go forward Let's now look into the ABCD matrix of a thin lens. And how do we start here is that we start by recalling the thin lens equation. So that's basically 1 over S naught, or SO as in S object, and plus 1 over SI as in the image equals 1 over S or 1 over S prime, using the kind of more familiar notation we are using for the input and output vectors in this course, equals 1 over F. That would be the focal length of our system. So this picture hopefully clarifies what are the variables if you have forgotten our basic optics course. So basically, SO is the distance of our object or point of interest. That's the kind of like a point from where the ray starts propagating, and the distance is into the principal plane of our thin lens, and that's the SO. And then SI is essentially the same thing, the distance from the principal plane of a thin lens all the way into the image plane where we are having our output ray emerging. So that's then this separation here, and the F equals the focal length of the lens. So that's basically how we describe a thin lens. Please note also that the relevant angles here are really small, so paraxial approximation holds. So in this case, the S parameter, so basically the object distance from the principal plane of the thin lens S, that can be written by looking at the figure, for example, that's y over tangent of alpha. For small angles alpha, that's approximately y over alpha. And using this, we can simplify things into a linear form. So with that, we can really build a matrix easily out of the math. So here, plugging that into the equations, we can write that the thin lens equation is of this form. So essentially, we take S and we replace this y over alpha into here, and we do the same thing for S prime, and we get this condition, and now we have a condition of thin lens in under paraxial approximation. So essentially what we get out by doing the math is that we can write that the output vector is equal to ABCD matrix multiplying the input vector, and doing the math correctly, we can describe that the ABCD matrix for a thin lens is essentially of this form. So we have a unity diagonal, and here on this C term we have 1 over F minus, telling us that something actually happens for the angle. Now let's go the same introduction and understand how mirrors behave. So let's consider, for simplicity, spherical mirrors with a radius of curvature r that can be then modeled essentially as a thin lens with a focal length of f equals r over 2. And please note that's the picture showing how all the variables are being defined. So that's the center of the radius of curvature, f focal length, o the object point from which we are looking at the ray propagating, then the ray refracts, and then we are hitting with the ray the image plane at which we are looking, that this is the kind of output plane of our system. And then these variables SO and SI again tell us the distance from the object into the principal plane of the mirror, similar as in the case of a thin lens, and then SI tells us the distance from the principal plane of the mirrors all the way to the image plane in an analogous manner as in the case of a thin lens. Please note that the R is positive and F complies with the convention that when the F is positive, we have a concave mirror, and when the focal length is negative, then we have a convex mirror. So that's basically the kind of notation we have here in terms of the positive and negative valued numbers. The ABCD matrix for a spherical mirror is basically represented in a way that we just replace the ABCD matrix of a thin lens, and here we plug in this condition for F. So that's basically the thin lens ABCD matrix, but now we replace the focal length of a thin lens with the focal length of a mirror. So that's how things go. And please, if you ever stumble upon ABCD matrices of mirrors, please do note that the propagation direction reverses. So we first have a propagation of ray propagating along the positive Z direction, but after hitting the mirror, of course, we will have propagation along the minus direction. So please be noted that if you really need to be describing ray propagation using mirrors and really mirror matrices, then please be careful keeping right track of the ray propagation, in which direction the ray is propagating with respect to the z-axis, positive or negative direction. And then finally, we start generalizing. So what happens when we have even more complicated cases? Or do we still have mirror slides? Okay, we do have. So if the radius of curvature of a spherical mirror goes to infinity, the mirror becomes a planar mirror. So this is the kind of final case of ABCD matrices for mirrors. So we have something described in that figure. And in this case, of course, the ABCD matrix, we can simply take the R to approach infinity, and we can write simply the ABCD matrix of a planar mirror as an identity matrix. So this is what happens when we are letting the radius of curvature tend to infinity. And like I already warned, naturally, we must still keep track of the propagation direction. So planar mirrors, even nothing seems to be happening for the actual ray propagation because we are multiplying a ray with identity matrix. Please note that, of course, the propagation direction is being reversed. So planar mirror turns propagation direction towards the minus z direction. This is an obvious thing, but easy to lose track of this if you're just simply doing the math and not thinking about the physics of your situation. And now we actually go into generalizing the ABCD matrices for optical systems. So let's now turn our attention to systems that consist of several components. So basically, this is the kind of final stretch that we can understand how a laser resonator is being formed and how a laser resonator behaves. So especially, this is extremely useful when we want to understand how stable a given laser configuration is. So essentially, facilitates stability analysis of a laser resonator. Now, propagation through an optical system can be described in a similar manner as before, but we just now have multiple matrices. So we describe propagation using a sequence of individual ABCD matrices, each representing an optical element in itself. And please note, like this is the picture, what happens. So basically, we now have a kind of generic optical system, and the total matrix, ABCD matrix, is essentially a multiplication of multiple element ABCD matrices. And please note that this, of course, is an ordered multiplication, as is the case when we are dealing with matrices. So we really need to be careful in which order we are multiplying the vectors. But if we do this proper ordered multiplication, we get a composite matrix that describes the net effect on the input ray. So we can really describe how a one single plane propagates a through pretty complicated generic optical system all the way into the image plane of interest. By just after we have made a decomposite matrix, by just multiplying input ray once with the total matrix of the system to get the output matrix. So we don't really do all these matrix multiplications all the time. It's just enough that we calculate the effective total matrix once, and then we multiply the input rays with that total matrix. Let's now go through the actual math, how we can really see how these matrices are being calculated so that you can really believe that this approach works. So let's calculate the relation between the input and output rays using this ABCD matrix formalism. So we have an input vector, we are multiplying that with the ABCD matrix of our system, and we get an output vector, so that's the primed variable vector. So we need to reconstruct the full path of the ray from end to start. So essentially, we just plug in all the matrices of interest of how many components we have in line within our optical system, and we start by having input ray multiplying the first matrix. And we can do the matrix multiplication, so we can multiply all these matrices together. And of course, we will get the composite matrix simply as in this form. So basically, by just explicitly writing the total transfer matrix, of course, it's basically this multiplication of all these matrices in order. And please note that these ABCD matrices of simple components, in a way, we must multiply them in a reverse order with respect to the physical sequence in which they interact with the ray. But basically, there is nothing surprising here. Like the order is just such that you start with the input ray, and then you multiply first with the matrix of the first element the ray hits. And after that, you will have an output ray, and that output ray then interacts with the second element and so forth. So this reverse order is like exactly just following the physical understanding how the rays are propagating. So in that respect, there's nothing weird, but just be careful that you understand at which order you multiply the input ray with the matrices, so that you somehow don't end up writing the total matrix in the wrong order, because multiplying matrices, the order of multiplication really matters. Then, in some cases, it's extremely useful to calculate the determinant of the system matrix, and that's given by calculating the determinant of the matrix ABCD, and that's essentially given by N2 divided by N1, where N1 is the refractive index of the medium we begin with, and N2 is the refractive index of the output medium. So essentially, that is a little bit weird of a result, but it helps in understanding how the kind of brightness of a bundle of rays is being changed when we are having rays propagating through the system. And related matter, if we have a unity determinant, that implies that the optical system does not contain any losses. So basically no absorption is taking place within the elements of the system. And then propagating beam quality is preserved. So essentially a parameter or a quantity known as attend is conserved. So this is basically what happens when we have a unity determinant. So this is more useful quantity when we are dealing with a kind of like non-imaging optics. So for example, we would be understanding how a kind of like a street light should be, or the mirror system guiding the street light lamp emission, light emission into the street, how we could optimize that kind of system. So attend is an extremely useful parameter when we are trying to understand like a non-imaging incoherent optical systems. Of course, attend is extremely interesting also in some cases when we are looking at the kind of like brightness of lasers. But on this course, I don't think we are actually like using any further use of attend as a variable. But I just wanted to mention here that this kind of variable or kind of physical quantity exists, and these kind of ABCD matrix calculations can be related to this variable. But if you're interested, please check out what Wikipedia has to say about attend and how that relates into optics. And I think we are now done with the first lecture on chapter 3. Yes. So I thank you for your time, your patience, and please follow me quickly regarding the next lecture that concerns Fabry-Perot interferometers on course of laser physics. Thank you and bye-bye.